Thanks so much for having me. In this talk, I want to tell you guys about what gRPC is, why it's a great fit for Swift in particular, and maybe a little bit about how you can use it. But first, how did I get to use gRPC anyway? Hang on. I think it's my system. It's not you guys. Okay, I think now it should work again. Yes, sorry. All right. So I used to work at Google for about 2 years, and I left to finally make my side project Timing into a full-blown time tracking app and make that my whole source of income. But once I finished releasing the first version, the next big challenge was actually creating a sync service for that app. And Timing is special in the regard that it's an automatic time tracking app. So unlike a regular time tracking app, which would create one data point every few hours when you start or stop a task, I generate several data points per minute. So I need to keep syncing all day, every day, like once every few minutes, essentially. And the first time somebody signs up for sync, they might upload all their data at once, which can be up to 30 megabytes and 100,000 data points. So it's quite a lot of stuff. And I wasn't particularly keen on uploading all this data with thousands of HTTP calls one by one, calling them in a loop, uploading stuff. But I was also not too confident in uploading 30 megabytes of JSON at once and hoping that it would all arrive in one piece online, because if somebody's on a bad or spotty connection, the connection might get interrupted before that upload is ready, is finished, so you have to start over again. So you need some way of batching things, but also some way of chunking things. And at Google, we already worked on an internal RPC system that was similar to gRPC, so I had some idea of that. So I looked at it, and it turns out that it actually supports streaming RPCs, which is essentially uploading chunks bit by bit without having to reconnect over and over again. But what is gRPC actually? gRPC is an open source messaging system based on Google's internal API architecture. It's used for generating your code and your documentation, for managing your APIs if you need that, and for serving your APIs and your microservices from a very small up to a very large scale. And of course, it also supports all of this on the client side as well. It's actually based on HTTP 2 below that, so it's fairly generalized. There's not too much magic going on. This is how your data structures look like with gRPC. This is an interface definition language called protocol buffers, where you essentially just define your types with the message keyword, then the name, and then you have fields inside these types where the type of the field comes first, in this case string, then the name of the field, and finally a field number. The serialization actually does not use the field name, but the field number, so you can rename your fields as often as you want. You just must never change that number. Protocol buffers also includes a wire format, so how to serialize this data, so you can transmit it over the wire, and also libraries and runtimes to do this in many, many languages. Essentially all the languages that you can think of support protocol buffers. And they go to great effort to actually make this feel native in every single language. So this would be the data types, but there's also actually serving your requests and responses. So that's where the service definition comes in. Essentially, you list all your RPCs, which are just methods. Then you provide one type of the kind of request that you want to get, and what the response will actually be, what its type will be. And in Swift, this actually looks very similar. So your call handlers or your clients aren't just sending any JSON data, so you don't have to serialize stuff into JSON yourself or into protocol buffers. all the decoding and encoding is done transparently for you, and you just get the request object, do something with it, create a response object, and return the response object, and everything else is being done for you. So it's very type safe and feels very native, as opposed to unpacking and depacking, packing and unpacking HTTP structures. And it has quite a few advantages over REST and JSON, of course. First of all, you don't need any more boilerplate, because all the code that you need is generated for you, both on the client side for calling your RPCs, but also on the server side for serving them. Essentially, you only need to implement the business logic, and the boilerplate of actually serving that and the routing is done for you. So you don't need to write a single line of routing code, for example. As I mentioned before, it's also type safe. You don't have problems with renaming fields or accessing them through strings. Everything is a Swift property, and you access them as you usually would, and you immediately get the correct type. So you don't have to guess the type of anything. You know all of this beforehand. It's also very efficient, especially when compared to JSON. The wire format is much smaller than JSON usually, and it's also more efficient to decode and encode than parsing JSON or building JSON strings and escaping them. It's also polyglot, which means that we have client libraries for almost every language for gRPC. So your Swift service can talk to your Java service or your Python service, or your Go service. They can all talk to each other as if they were written in one language. Like, it doesn't really matter. With Swift and Codable, you're getting somewhere in that direction, but if the other endpoint expects your dates to be formatted in a different format, things like that, you still have these interoperability gotchas. And with gRPC, you don't need to even write your codable structs. You write your service definition once and your protocol buffers, and then you're done, and you always have that as the one single source of truth that all your services will understand and accept. It's also pretty good for error handling. You don't need to look up, like, where do I find the error message? Is it in the message field or in the error field or something like that? gRPC provides standardized ways of sending your error messages or even additional data with your errors that you can then handle and react accordingly. And on the client side, these mostly or almost feel like throwing. So you get the errors the way you expect to get errors. And Swift and gRPC are a great fit for mostly three reasons. The static typing that I mentioned, the efficiency, it's way faster, and you don't write Swift on the server because it's like super dynamic and slow, but because it's fast and you need the performance. And finally, it's polyglot, because we can't yet expect all the services that we interact with to be written in Swift, but with gRPC, we can essentially talk to any other gRPC service written in any language. Here's a slide showing how the polyglottiness works in practice. We have a gRPC stub running on your phone or on your Mac that can then talk to your gRPC service on the server, which can be written in Swift. And that Swift service then can call even more backends in case you already have large-scale deployments. And those backends can be written in Python, Java, C++, whatever. And they all work seamlessly with each other. And in fact, what's also nice about this is that if you have an API that you want to talk to, but you don't have a client library for that API, so you would usually need to write your codable structs, you can just compile their gRPC service definition into Swift, and you essentially have a client library that feels native for any gRPC service that you can ever look at, that you ever want to work with. Let me illustrate how this works in practice with the timing sync service. First of all, we have the Swift gRPC client running on macOS in the user's app, which talks to, is the sound off or? Sorry, which talks to endpoint service proxy, which is essentially a proxy that can be used for API management by Google. It can also transcode HTTP1 and JSON to gRPC. So if you have still some legacy clients that actually want to talk HTTP and JSON to you, you can do that with endpoint service proxy. Then we actually have the Swift gRPC server running in the cloud and serving all of this. The database access is done through Cloud SQL proxy, so this is all running on Google Cloud, and this essentially proxies to a managed Postgres database, which I am accessing through Vapor and Fluent. And all of this is hosted on Kubernetes. So you just deploy the gRPC server together with the SQL proxy and the endpoints proxy for transcoding. If you need that, you can of course also leave it out. I'm also talking to a few other services. For example, I'm using Cloud KMS for encryption and key management. Currently, I'm talking to that using REST and OAuth, which is not very nice because you have to do all this OAuth flow, all the back and forth. And I also had to write some codable structures for the communication and set up the HTTP client myself. I had to do this because back then Cloud KMS did not actually have a gRPC interface. They now have, and the gRPC interface actually accepts for authentication JWT tokens that you can sign yourself. So you can skip the OAuth. You have way lower latency because once you have established a connection once, it will stay around for almost indefinitely. And you can use gRPC, which feels much more native. That just hadn't been around back when I used it. I'm also using Postmark for sending emails. They have a REST interface, but if they supported gRPC, I could essentially just generate a client library for their interface instead of having to build that myself again with Codable. So all the red arrows here are places where you could actually be using gRPC or protocol buffers to make your life easier. Next up is Stackdriver logging, which just aggregates my logs and makes them searchable. I send that by essentially just printing JSON to a standard output, which then gets parsed. And you can actually even use the standard JSON format they have with the protocol buffers library to essentially fill in the JSON in a type-safe way, then tell the library to serialize that as JSON and then just print that. Again, saves you from writing your codable structs yourself. We also use monitoring, which essentially the endpoint service proxy and the logging talk to automatically. And finally, I've also written a very small tracing library, which collects traces from inside my app and which sends these over through gRPC to Stackdriver trace. So I just collect all the traces and that occur, and every 10 seconds I send all of these at once to the tracing service with one gRPC call. All right, so much about the tech stack that I'm using. But in general, how do we now combine Swift and gRPC? Because gRPC is a protocol, we somehow need to implement it and we need to use it. And luckily, we have Swift Neo that can do a lot of the work for us. I guess by now everybody knows Swift Neo here. Anybody? Great. So it's just a very efficient way to do a non-blocking I/O in Swift, and almost all the server-side frameworks supported by now. So it's great for interoperability because if one of your frameworks or if one other framework uses Swift Neo, it's very easy to integrate it with your event loop and just to talk to that and use it, like have the database calls on the event loop as well. Swift Neo also includes HTTP and HTTP2 stacks from Apple, which is good for us because we get a ton of stuff for free. Like we get the underlying transport layer for free. We get SSL support for free. They even provide security fixes. There have been some issues with HTTP2 recently for there were some denial of service attacks that were possible on the H2 protocol, and the Neo guys essentially fixed these for us, so we didn't have to do any work ourselves. So we use this for gRPC Swift. We currently have an old version of the code on the master branch that's still based on gRPC core, which is a C library that does gRPC and HTTP2. It does a ton of stuff, but it's actually overkill and it doesn't play nicely with event loops. So if you want to get started with this, especially on the server, you actually want to check out the Neo branch, which is a clean room implementation of gRPC on top of Swift Neo HTTP 2. It's actually a great way to, if you want to understand the gRPC protocol, you can just look at our channel handlers, like how we encode these, how we put essentially the bytes on the wire, because the protocol itself is not that complicated, and you can just look at what we do. Essentially, it's message lengths and then the serialized protocol buffers. Yeah, and the nice thing is also that it has backing from both Apple and Google. Google originally initiated it, and Apple now has a full-time employee dedicating a lot of their time to it, and they put a lot of work into it. So I guess they are planning to use it in production, which means that they have a strong interest in this stuff actually working. George, who's actually working at Apple on this, who's sitting over there, recently submitted an excellent proposal to the Swift server working group. So we are looking to be fully endorsed at some point, and we want to put in all the work that's necessary for that. For example, we already use Swift logging as well. You can have a look at the proposal if you want to at bit.ly/grpc-proposal. And you can, of course, at any time just check out the code and play with it at github.com/grpc/swift. Just make sure to use the Neo branch. And the project is actually pretty far ahead already. We have client support, so you can talk to gRPC services. You just need to provide an event loop where your requests are handled on, and then you will get a future back for your call, essentially, and you can use this data. We have serving support. So essentially, we do the serving for you. You just need to implement your business logic. We have SSL support that includes clients talking to HTTPS servers. It includes serving HTTPS on the server side, and it also even includes client certificates. So if you want to have strong authentication of your clients through certificates, you can just provide them to the Neo stack, and you will have all this SSL authentication being handled for you on the low level, and usually it just works. We've also taken great care of providing good documentation and examples to help you get started as quickly as possible. And we're very keen on having good test coverage as well, because we want this stuff to be able to be used in production and to behave in an expectable fashion at any time. We're already supporting Mac, Linux, and iOS as the platforms. I think that tvOS should be supported as well. watchOS I'm not quite sure about, because their networking stack used to be a bit peculiar, but that might have become better with watchOS 6. Also on iOS, we get the Neo transport services for free, for example, which makes background transport much easier, similar to what NSURL session did for HTTP. One thing that we still need to add is middleware for additional authentication or error logging and things like that. We have some ideas for that, but we should be able to add those after version 1.0. All right, so much about the theory. Let's have a quick look at how this is actually going to work in practice. For this, first of all, a few, hang on. One moment, okay. So, first of all, you would clone the repository as you usually would to get started with it. Or, of course, you can also depend on it with Swift Package Manager. You move into that directory, and then what you actually will need to do is to install the protocol buffers package, which includes the protocol buffers compiler. I've done this already, like protobuf is already installed on my machine, but once you've installed this with Homebrew, you already have the protocol buffers compiler that can compile your service definitions into Swift code that you can use in your code. Next up would be creating the plugins for the protocol buffers compiler. These are essentially what is needed to generate Swift code specifically from your interface definitions. Then we copy over our these two binaries to somewhere in your path so that the compiler can find them. And now we can actually invoke the protocol buffers compiler to convert the .proto files into Swift files. First, we move into a particular directory in like one of these examples to compile these. All of this is, of course, also documented on GitHub. They tell you where you should look to get started. And when we're in that directory, we can compile the protocol buffers interface definition into Swift code. So we have a few arguments to this method. First of all, we tell the compiler where to output Swift files for protocol buffers. Then we tell it where to output the gRPC specific stuff, which means the actual service stubs, which includes, for example, test stubs, where you can just say, okay, if the client calls you, just return this response or this set of responses. This makes it very easy to test how your client responds to a particular input, and also to make sure that the client sends the things to the server that it should be. So you don't have to write mocks yourself. We provide some basic ones for you. The next two options are just about to make sure that the code is actually public instead of internal. If you are going to use that code in the same module as the rest of your code, as the code that accesses it, you don't need that. But if you want to put all your gRPC code into a separate module, you will need the public visibility, again, for both Swift and gRPC. And then finally, you just provide your service definition, and the compiler will generate these Swift files for you. Once we've generated these, we can actually run them as we would expect to. So first of all, we run a gRPC server. That's built now, and it's running, and it tells you the port that it's running on. You can, of course, also pick a port yourself. Then in a separate terminal window, we are going to run the client. And that needs to use the port that we have just been told about. And the client will automatically connect to the gRPC service, send it a request, wait for its response, print out the response, and exit. And as you can see, we've got a response, and we can also provide a different name that will be sent to the server. The server will take that and send you a different response back. And finally, you can, if you're still on Xcode 10, create an Xcode project with all the correct formatting for you. You could also, of course, use the regular generate Xcode project. We just do some additional formatting options to make sure that that your spaces, for example, in the project. And then finally, you can open the project. Let's have a quick look at the code. First of all, we will look at how the server is working. So this is the entire server code. It's 50 lines of code, where 20 lines are license and import. First, we just set up the logging system to mostly suppress the logs. Otherwise, you get a lot of logging statements, which helps with debugging. But you can, of course, disable all of these. Then we just set up an event loop group, because the server needs that to know where it should actually serve requests on. Then you provide a configuration for the server, which just tells it which address to listen on and which port. If you select 0, it will pick a port for you, otherwise you can provide one, which event group to serve on, and which services to actually serve on. I will get to that in a minute. This is actually where the actual the real stuff happens, and then we just tell the server to start, and that gives us the future that will be fulfilled when the server has actually started up. Then we actually just print out which port this server is now listening on, and finally we just wait on the future that tells us when the server has shut down. And then the service would quit. And the interesting part is actually the greeter provider, which is the stuff that you are actually going to implement. And this just implements the Hello World greeter provider protocol, which is the protocol from the generated code, which includes all the methods from your service definition with the request object, with all the data encoded in a nice type-safe fashion, a context, which has additional HTTP headers if you need them, or if you want to return a particular status code, you can also all provide them to the context. But other than that, you're just expected to return a future with your reply object. These objects are also good citizen Swift value types, of course. So we check for the name in the request. If there is one present, we return that name, and otherwise we just use stranger. We build a string with that, we build our response, and then just we return a succeeded future with our response. If you were now using Vapor, you could of course just use that. You could of course map futures onto futures with database calls and so on, and just return the final future, and we will make sure to serve that for you once all the work of actually fulfilling the request has been done. The client is very similar. It's, again, setting up the logging system, then just some startup code like parsing the arguments to know which server we are supposed to connect to. Then we have a client configuration, which in this case connects to localhost, and the port that we provide on the command line. And again, an event loop group, that's about it. If you want SSL, you have an additional field there to provide your SSL certificates. Then we create one client connection and provide this client connection to a service client for this particular service. The reason why these two are split up is because you can host several gRPC services on one particular machine, like on one endpoint. And if you want to do so, you can share the connection to that endpoint for all the services that are actually being hosted on that service. And finally, we just call the greet method, and that is actually what is using our service. So we generate our request object again, and we just fill in the name field, and then we just call greeter.sayHello request. And what this actually does is it does all the magic of the RPC call under the hood, return these to you, and return a future for you. And then we just wait on the future with the response. You can also wait on a few other things like status codes and so on, but most of the time you will actually be interested in the response. And if the call errored for some reason, the response will be fulfilled with an error. And then we just print out the message we get in the response. And that's about it. And one more example of how we can show you this, how you can use this in conjunction with Vapor. Essentially, all you need to do is put an extension on the request class from Vapor with a convenience initializer that takes the application class and our gRPC server call context object. This is the one that gets passed on to all of your providers, like all the methods that we expect you to implement. We will give you this context, and so you pass your application, which you just store in your provider as a singleton, and the context to initialize a request. Most of these fields can be filled in from the context, and then finally You just create the request object in each of your provider methods, and then you have a request object, which is a Vapor service container. So from there, you can use all the Vapor services, including Fluent and so on, like you would usually, just by telling the request to provide an object of the desired class. If you want to now get involved with the project, you can of course try it. I already told you the URL. If you're using it, please tell us. It's always good to know where the project is being used and to have like some sample use cases that we can point to. Same if you already have a gRPC service that you want an API client library for, try to build it with the project. It should be fairly easy. Let us know how it goes, or if you got sample code for Swift gRPC yourself, let us tell us. And we're also very much looking for feedback. So if there are things that we can improve, please tell us. If there's things that you actually need to be present for you to use gRPC, tell us as well so that we can add these things. And we are also very happy about any feedback that we can get for our Swift Server working group proposal. And if you want to provide PRs, we're happy to take them. So thank you.